In lecture number 10, we have discussed about the fundamentals of the flexibility matrix method. And further, in lectures 11 to 14, we have discussed some fundamental results which help us in developing the flexibility matrix and the displacement vector. Now, essentially, the flexibility matrix method is solution of this equation. Delta is the final displacement at certain joints in a structure. Delta L are the displacements at the same joints due to externally applied loads on a release structure, and delta R are the displacements in the same joints but due to the unknown forces chosen in the structure as redundants. Now, essentially here, R represents the redundant forces, delta represents the structure flexibility matrix. So, delta R can be written as delta matrix multiplied by the unknown force vector or the redundant force vector. Now, to illustrate this equation further, I am going to take an example of a continuous beam, two-span continuous beam like this. Essentially, we know that this equation is a compatibility equation or a compatibility condition. Now, we are going to solve this problem, which is statically indeterminate, through flexibility matrix method by solving this compatibility equation. To start with, we have to find out what is the degree of static indeterminacy of the structure, and we know that ds for this structure will be equal to 3 times number of members plus number of reactions minus 3 times number of joints. That is equal to 3 into, there are just 2 members in the structure, number of reactions 3 plus 1 plus 1, that is 5. 3 into number of joints is equal to 1, 2, 3. This number is 6 plus 5 minus 9 equal to 2. And we can identify those two unknown forces or those two unknown forces here as the moment at support A and moment at support B. That is a choice of the unknown forces. We can also choose the reaction here and the reaction here as unknowns, but for the time being, I am going to choose the moment at this support. Let us say MA clockwise, and the moment at this support, say MB, as the unknown or redundant forces. So the vector R will contain, let us say in general, R1 and R2. In this case, they are equal to MA, that is the bending moment at support A, and MB, the bending moment at support B. Now hereafter, I am going to use the symbol R1, R2, R3, etc. as the elements in this vector, capital R. Now, after choosing the unknown forces as MA and MB, we can draw a release structure or a statically determinate structure. If you remove the moments MA and MB from the structure, this will become statically determinate. If you draw that, that is the original structure, supports A, B and C. Now, if you remove the moment from A and B, we are going to have hinges over here. This point becomes a hinge. This point also becomes an internal hinge, like that. So, the span AB and span BC are going to behave like simply supported spans. Now, if I apply the external loads over here, say 4 kN/meter over here, and this load 10 kN. So we can call this as the release structure with external forces. Right. Now, I can call this, say, unknown moment MA as the coordinate 1. Corresponding to this MA, I can choose a coordinate. So let me draw the coordinates maybe in another picture. That is the structure. This is the internal hinge introduced. Now, this is a coordinate. Let me call that as 1. This is another coordinate. Let me call this as, say, clockwise here and anti-clockwise here. The reason is the moment at this support in the span BA, if that is clockwise, the moment at the same support in the span BC will be anti-clockwise for equilibrium. Following sigma m is equal to 0 at this joint, the moment in the left span and the moment in the right span are going to be equal and opposite in nature. That is why when we choose coordinates corresponding to the degree of static indeterminacy, 2 in number, this as, say, coordinate number 1, and whenever we choose a coordinate in one of the internal supports like that, we mark it by 2 arrow marks, one like this, one like that. You can also choose this arrow mark the other way, that is anti-clockwise, and this arrow mark clockwise. If one is clockwise, the other should be anti-clockwise. So this is the structure coordinates. Release structure with structure coordinates. Structure, or sometimes it is also called as system coordinates. Alright, now we have to establish this flexibility matrix, which is also called as structure or system flexibility matrix, and this displacement vector delta L, and of course this delta vector. This delta vector is it will contain the applied displacements corresponding to the joints A, B, C, etc. Now here we have chosen the coordinates at joint A and joint B only. So the displacements applied displacements corresponding to joint A and joint B are going to be the components of this vector delta. And since there is no support movement or support rotation given in this particular example, delta will contain 2 zeros. That is, the applied displacement corresponding to coordinate 1 and that corresponding to coordinate 2 would be 0 in this case. Now, to establish this delta L vector, there are 2 components in delta L vector. Let us call the first one as delta L1. Delta L1 is the rotation corresponding to coordinate number 1 due to the externally applied forces at joint A in the release structure. That is, the rotation corresponding to say coordinate number 1 in the release structure due to external forces. Now, if I plot the deflected shape of this structure, I told you this will be behaving as a simply supported span. This also is going to behave as a simply supported span. So this will be a possible displaced configuration of the structure. The rotation at this end is going to be this angle, and rotation at joint B would be sum of these two angles, sum of this angle and this angle. So delta L1 will be this number, rotation here. Delta L2 would be sum of these two angles. Now to find out this delta L1 or this angle, we know that if we have a simply supported span with loaded by UDL throughout, the rotation at the supports, they are equal, and if loading is W per meter, span is L, the rotation at the supports are equal to W L cube divided by 24 EI, which is derived in the previous lecture. If I just adopt that result over here to find out this rotation, W will be 4, span is equal to 3 meters, 24 EI. Now with regard to the direction, the coordinate assumed here is clockwise, and rotation here is also clockwise. So this will be having a positive sign. That is delta L1. Further, delta L2 is equal to sum of these two angles. This angle will be W L cube divided by 24 EI. We have assumed this coordinate as clockwise, but this rotation is anti-clockwise, so we have to put a minus in over here. Now this rotation, this is clockwise, but the coordinate here is anti-clockwise, so we have to put a minus sign. And this rotation, because of a central point force in a simply supported span, would be given by W L square divided by 16 EI, derived in the previous discussion. So I am taking the result over here. W is 10, L is 4 meters for that span, L square divided by 16 EI. So this is delta L1 and delta L2. The numbers are 4.5 divided by EI, and this is minus 14.5 divided by EI. That is about delta L vector. So we have developed delta vector, which is already having zeros as the components. Delta L vector having components. If you take 1 by A outside, the components are 4.5 and minus 14.5.